Good morning. Okay, we started with the, we stopped at, I hope you're all doing good. And we stopped at Lewis structure for sulfur dioxide yesterday. We are going to have other examples of Lewis structures and resonance structures. Before beginning that, do you have any questions for me? Okay. No questions. So we have the another example for Lewis structure. Let's say we're going to take the structure for acetate ion. So if we have CH3, CO2H, losing one hydrogen is going to change to CH3, COO minus, acetate ion. Lewis structure for this molecule. The backbone of the molecule in organic compounds, your carbon-carbon bond is going to form the backbone of the molecule. So we have CC. For the, okay, I have to find a way that I can only erase one part and not everything. CH3 COOH minus H. CH3CO O minus. Okay. The backbone of the molecule, we have the C and then oxygen. One more oxygen here. To find the to draw the Lewis structure, what was the first step? Do anyone remembers the first step for the Lewis structure? Which electrons are used for Lewis structure, for drawing Lewis structure? Drawing the bonds? Okay, thank you. We have to calculate the number of valence electrons. So we have carbon, 2 carbons, so that would be 2 times 4 for 4 valence electrons. And we have 2 oxygens, 2 times 6. And we have 3 hydrogens. That would be 3 times 1. Total number of electrons is going to be 8, 20, and 20, 23. There is a negative charge here. For the negative charge, we need to add 1 more electrons. So plus 1, that's going to be 24 electrons. We start with 24 electrons. We are going to, the first step that you already, very good, you already respond, we need to connect them. So there should be a connection between the atoms. So we have 1 carbon-carbon, 3 carbon hydrogens, and 2 carbon oxygens. How many electrons did I use to connect them? 1, 2, 3, 4, 5, 6 bonds. So that is going to reduce 12 electrons. So we're going to subtract 12 electrons, and we end up with 12 electrons remaining. What's the next step? Who is getting electrons first? Carbons or the side elements? The side elements. Does the hydrogen need an electron? Hydrogen is satisfied with 2 electrons, so it doesn't need another electron. Very good. And we are going to give electrons to oxygen. We have 2, 4, 6 required for 1 oxygen, and then would be 2, 4, 6 required for another oxygen. So 12 electron is gone. 0 electron is left. Are we done with our structure? When we are done with all the electrons, when there is no electrons left, we have to go to the molecule to make sure every element is satisfied with the 8 electrons. Now we have this oxygen here, oxygen 1, I'm going to call oxygen 1 is satisfied, oxygen 2 is satisfied, carbon 1 is satisfied, carbon 2 is not satisfied. So what would be the solution? The solution is to take a pair of electrons from one of the oxygens, bring it to the center, and do multiple bonding. That's where we stopped yesterday, but using multiple bonding as a solution to get every element satisfied with the 8 electrons. So oxygen 2 is giving electrons. What happens with the oxygen 1? Oxygen 1 has 3 pairs of unshared electron, 1 pair of shared electron. Oxygen 2 has now 2 pairs of unshared electron and 2 pairs of shared electron. That's one structure for the for one correct Lewis structure for acetate ion. And if we were going to draw the second structure, we have another oxygen that can give actually pair of unshared electrons or donate electron. So we use that second option when oxygen 1 is going to give pair of electrons. So we have our one structure. And the second structure. Okay. Now, what's the benefit of having 2 resonance structures? Resonance structures is going to stabilize the molecule. So how is this going to stabilize the molecule? The stabilization of the molecule is moving the plus charge from one element to another element. If you can distribute the plus charge among 2 different elements, it's going to make the molecule more stable. And where is that plus charge or the negative charge that we have? We have to calculate the formal charge for the elements and see the charge distribution and find out how it's going to be distributed. And if the plus charge or plus and minus, if the charges are distributed, then it's going to benefit the molecule because it's not just one element carrying the plus charge. So the resonances is going to stabilize the molecule. One rule you need to know, the greater number of resonances, the more stability for that compound. So now it comes new topic, and that new topic is calculating formal charge. Why formal charge? Because for organic molecules, we do not have charge. Ionic compounds like sodium chloride, sodium has plus charge, chloride has negative charge. When it comes to organic molecules, because bonds are forming based on sharing electrons, so there's not going to be transfer of electron, but we could still calculate formal charge. When we are calculating formal charge, we are comparing that element. If it's standing alone, like in periodic table, how many valence electron is going to have compared to when that molecule is actually when that element is inside the molecule, how many electron is going to be assigned. There is a simple way, is just boxing the element with number of electrons that has, and there is a formula. So I'm going to use both. So let's say if I box this oxygen here, if I box this oxygen here and count how many electron, if I was going to take this oxygen away, how many electron would I take this with this oxygen? There are two pairs of unshared electron and two pairs of shared electrons. So if we are cutting this bond between the carbon-oxygen double bond means 4 electrons. When we cut it down, we are going to divide the two bonds into between the carbon and oxygen. So 2 electrons from shared, and then we have 4 electrons from unshared. How many valence electron oxygen has when it's in the periodic table? Whereas in periodic table, 6. In this molecule is also 6. So comparing the number of electrons towards in the valence electrons is the same. So the charge is going to be 0 for this oxygen. What about this oxygen here? This oxygen here is going to have 2, 4, 6 shared electron. I'm sorry, 6 unshared electrons, 6 and 2 shared electron. When we box it, is going to cut the number of shared electron in half between the carbon and oxygen. So this oxygen is going to have 7 electron, and with the 7 electron comparing to 6 valence electron, it's going to be 1 minus charge here. So we are getting 1 minus charge. What about the carbon here? This carbon is going to have, we change the box color. So if you look at this carbon here, carbon has 2 from this side, 1 and 1, 4 valence electron, 4 electron inside this molecule is going to be 0 charge. The other carbon, second carbon, is going to be 0 charge, and is going to hydrogens. What's charge for hydrogen? Formal charge for hydrogen. Can anyone respond with the formal charge with hydrogens? Very good. 0. And there was a question, is it going to be 24, 23, or 24 electrons? That 1 electron came from the negative charge, and thank you for your own response again. That is not 23, is going to be 24 because of the negative charge. I counted 23 electrons, and then the negative charge that acetate molecule or acetate ion is going to carry, that is adding 1 electron to make it 24 electron. So going back to formal charge for hydrogen, here we have 0 for each of these hydrogens, because 1 electron is assigned based on the structure. 1 electron is the valence electron for the for hydrogen in periodic table, so it's going to be 0 charge. Now, formal charge for 1 oxygen is 0, 1 is negative, and formal charge for the other molecule, because it's very similar. If we box it out, it's going to be -1 for 1 oxygen, 0, and everything else is going to be 0. So we have everything 0, and there's 1 negative charge. Because it's a polyatomic ion, acetate ion, this 1 negative charge, it's unavoidable. It has to be there. And which element is more desired to take the negative charge, the oxygen or the carbon? So when we are distributing electrons and we calculate the formal charge, the more electronegative element, if it takes the negative charge, that is better loose structure. So I said one method for boxing out, and the other one is going to be using the formula. So the formal charge, if we say the formal charge for the let's say oxygen 1, going to use this one, oxygen 1, formal charge for that oxygen, for oxygen 1, is going to be number of valence electrons, which we have 6 for oxygen. So number of valence electrons for that element, minus all unshared electrons. So minus the unshared electrons. How many unshared electrons we have for this oxygen 1? If you can see it there, 6, and then minus 1/2 of shared electrons. Shared electrons. So we have 1 pair of shared electrons, and half of that is going to be 1. So I can simplify it, just say 1 here, or I could say 1/2 of 2, which is 1, and the answer is going to be -1. And that's what we have for the formal charge for oxygen 1. Formal charge for this carbon, just going to put carbon 1. Formal charge for carbon 1 is going to be 4 valence electrons minus 0, if you follow the formula, unshared electrons, because there is no unshared electron, I'm just using 0 here, minus half of the shared electrons, so it's going to be 1/2 of 8 electrons. We have 1, 2, 3, 1 bond on the right side, 1 bond on the left side, and double bond to oxygen. That's 4 bonds. 4 bonds means 8 electrons. Half of 8 is going to be 4, and the charge is going to be 0. Very good. Okay. Any questions about calculating calculating formal charges? Any question about drawing Lewis structure? In terms of the steps, if you have any questions about drawing the Lewis structure. So the only thing that we still have to deal with is like what is major resonance, minor resonance, and drawing resonances. When you are drawing resonances, you can only alternate or change the position of the pair of electrons and the pi bonds. So those are delocalized. The backbone of the molecule stays the same. And there should be a benefit for the molecule to form the resonance. Like in these two resonances, we have the negative charge carried by oxygen 1 in one resonance and negative charge carried by oxygen 2 in another resonance. So that is going to make the molecule more stable, because one oxygen is not the only oxygen who is carrying the negative charge. The more resonance, the more stable the molecule. So sharing, caring is the same thing. So here, basically the two oxygens are sharing the negative charge. At one point, one oxygen is carrying the negative charge, another point the other oxygen is carrying the negative charge. Which one is major, which one is minor? So is A major or B is major in this case? What makes the A or B major or minor? Which one is more stable? Let's say if you had a Lewis structure that carbon would carry the negative charge versus the oxygen, that would not be a stable condition. So in that case, we would say that resonance is going to be minor resonance or minor contributor, and is not, because it's not stable or is less stable. In this case, A and B, they are both stable or as stable. They are very similar in terms of the formal charges and distribution of the electrons. The more electronegative element in both cases is taking negative charge, everything else is 0. So both of them are major contributors. See, we have another example here. Okay, this is just example. These are just examples of another Lewis structure and counting. In Lewis structure, you show the pair of unshared electrons, but if you have pair of shared electrons, you would show it as the dashed line. If you're comparing the Lewis structure for methylamine compared to ethanol, compared to chloromethane, we talked about these Lewis structures and the pairs of unshared electrons yesterday. Methylamine has one pair, one lone pair. Alcohol has two, and alkyl halide, or chloromethane in this case, has three lone pair. What it shows that the more number of lone pair or unshared electron, basically it gives more reactivity to that molecule. So if you had CH4 here, CH4 with carbon with 4 hydrogen bonded, there is no lone pair anywhere. So that is the least reactive of the among all 4 of them. And chloromethane is going to be the most reactive because of the 3 lone pair that we have on the chloromethane. So this is kind of a pattern in organic molecules. Carbon is not supposed to have any lone pair because it's not stable. Carbon must have 4 bonds. We talked about carbon being tetravalent yesterday. And when we have heteroatoms, nitrogen, oxygen, chlorine here is called the heteroatom. That means these elements are not carbon or hydrogen. Carbon and hydrogens are the main 2 elements for organic molecules. Any other element, it counts as the heteroatoms. So normally, or the pattern for nitrogen in organic molecule is going to carry 1 lone pair, otherwise it's going to be charged. Oxygen, 2 lone pairs, and halides is going to carry 3 lone pairs, and that makes these molecules to be, these compounds to be more reactive. Okay. And being able to count, you get a question in the quiz and in the exam, being able to count number of lone pairs, number of single bonds, number of double bonds, how many sigma bonds and how many pi bonds. And I have to give you example of the sigma bonds and pi bonds also. Okay. So if you look at this, just again, common pattern, we see carbon, they have no pair of unshared electrons. Oxygen has 2 pairs of unshared electron, and here nitrogen has 1 pair of unshared electrons. Since we talked about number of sigma and pi bonds, and I said you will have the question, let's look at this example here. If you have a carbon-carbon double bond, for any double bond, 1 bond is called sigma and 1 is a pi bond. If you have carbon-carbon single bond, I should have started with this one actually. Is this a sigma bond or a pi bond? That's a sigma bond. So carbon-carbon single bond is 1 sigma bond. When you have multiple bonding, the first one is always sigma. So we have 1 sigma and there's only 1 sigma bond. Any additional is going to be pi bond. If you have a double bond, you have 1 additional bond and that is a pi bond. If you have a triple bond, you have 2 additional bonds and that is 2 pi bonds. So how many sigma bonds we have for ethylene? So basically, very good. So you're counting, let's count 1, 2, 3, 4, 5. So 5 sigma bond. And how many pi bonds do you have? 1 pi bond. So we have 1 pi bond and 5 sigma bonds. Sometimes students, the common mistake is that they don't count the sigma bonds from double bonds. There's like 4 sigma bond and then 1 double bond. Now, if the question is like how many single bond, how many double bond, it would be 1 double bond and 4 single bond. But when you are counting number of sigma bond, out of the double bond, one is sigma and one is pi bond. For this model, oxygen has 2 pairs of unshared, 2 pairs of shared. Carbon has 4 bonds, 2 single bond and 1 double bond. Total number of sigma bond is 3. So 3 sigma bonds and 1 pi bond. Okay. Questions. You had one question about what is halide. Is not a halide. I'm sorry. Is halide. Halogens, group 7A. Those are the elements that in group 7A as halogens, and when they are in the molecule, we call them like halide in general. But specifically, it would be chloride, bromide, iodide, and others. You're welcome. Okay, when the triple bond here is forming, this is the example of triple bond. How many pi bond and how many sigma bonds? Again, just to emphasize, we have just count the total number of sigma bonds for acetonitrile, please. 1, 2, 3, very good. 5 sigma. How many pi bonds? 2 pi bonds. And 2 pi bonds. And we have 1 pair of unshared electrons on nitrogen and no unshared electron on carbon or hydrogen. One point I have to emphasize from yesterday, I mentioned, but I want to make sure that everyone understands. The hydrogen cannot form more than 1 bond because it's in level 1 of the periodic table, has only 1 s orbital, has only 1 shell. So hydrogen can never have more than 1 bond. Because of that, the number of the orbitals that is available to hydrogen being in level 1 is only 1 orbital, 2 electrons. So it cannot be central atom, never. And then the halogens. Halogens, if you have like chlorine, bromine, or fluorine, they cannot be central atom either. Why halogens don't form more than 1 bond? Because halogens, they have very high electronegativity. Group 7 in the periodic table, they're very close to noble gas. They have the highest electronegativity in each row. And they don't like to share more than 1. They only share 1 because they only need 1 electron in order to form their octet or satisfy their octet. Halogens never form double bond. Just keep that in mind. Hydrogen cannot form double bond. Halogen don't form double bond, only single bond. And halogens or hydrogen cannot be central atom. And when you do have a choice of other elements for central atom, you look for the electronegativity. The element with lower electronegativity is a better candidate for central atom. Lower electronegativity. What does lower electronegativity means? It means that it doesn't mind sharing. It doesn't have very high tendency to accept electron. It has lower tendency to accept electron. That's low electronegativity. So it doesn't mind sharing. So it's going to be better candidate for central atom. So between sulfur and oxygen, which one is a better candidate for central atom? Is going to be sulfur, because sulfur does not has lower electronegativity and can form more than is in level 3 also. Sulfur being in level 3, it can form more bonds. It can even form more than 4 bonds if needed. But oxygen, because it's in level 2, cannot form more than 4 bonds because it has only 1 s and one p subshell, and total of 8 electrons. And because it's total of 8 electrons, cannot form more than 4 bonds. So it's tetravalent also, just like carbon. This is just something I remembered, and you will need it later. Okay, any questions about counting sigma and pi, or in general drawing loose structure? No. Minor and major. Okay, this is a very good question. Very good question. I will show another example with when the minor is actually being a minor. Let me just move toward the slides one more time. Let's see, just to make sure that we understand it. We covered about bonding yesterday. When we have a positive negative charge, that is ionic bonding. We have covalent bonding, and if the covalent bonding is between two same non-metal, is going to be non-polar covalent bond. If it's between two different non-metal or non-metals that they have different electronegativity, one has greater desire to accept electron, so it's going to pull the electrons to one side, and that makes it polar covalent bond. Why covalent? Because it's the bond between two non-metal. Nitrogen is non-metal, hydrogen is non-metal, so this bond is going to be covalent. Why polar? Because it's polarized. Why is polarized? Because nitrogen has higher electronegativity, is going to pull electron toward itself, and electrons is going to spend less time around hydrogen, greater time around nitrogen. And when you have lower electron density, it's going to be partially positive charge. If you have higher electron density around nitrogen, it's going to be partially negative. So if you look at this example of oxygen and hydrogen, which one gets the negative charge? Partially negative charge is not going to be solid negative charge, is going to be partially negative charge, is going to be oxygen here, because oxygen has higher electronegativity. Hydrogen would take the positive charge or partially positive charge, and we show that with this symbol of delta or sigma. Looks like both delta negative, that's partially negative charge or partially positive charge. So we have three different type of bonding. So we have the ionic bonding and non-polar covalent or polar covalent. So general trend is like two same non-metal is going to be non-polar, two different non-metal is going to be polar covalent, and if it's metal non-metal is going to be ionic. But if you were given the electronegativity value, if the difference between electronegativity of the two elements is less than 0.5, so if it is less than 0.5, is going to count as, yes, it's down here. So if it's less than 0.5, it's going to be non-polar. If it's between 0.5 and 2, the difference in electronegativity between 0.5 and 2 is going to be polar covalent. And if it's greater than 2, is going to be ionic. But general trend for organic chemistry, general trend works. So just know that the bond between carbon and hydrogen is non-polar. Any questions about polar, non-polar? So if you have, if it's a diatomic or if it's just a linear or the two atoms, you look for the electronegativity. And how would you determine if the molecule is polar or non-polar, and what is the benefit of that? If for a molecule to be polar, it must have uneven distribution of electron, just like a bond to be polar. But when you have a molecule, more than one bond is there, and you have to look for the overall distribution of the electrons. So you look at the central atom there. Because it's a review, I'm just going to show it to you now. It's the trick. So you just find the central atom and see if the central atom is connected to domain atoms or other atoms. Similarly, if they are exactly the same with the same number of same order of the bond, then your molecule looks symmetrical and the dipole moment is 0. That means your molecule is going to be nonpolar. For a molecule like CH4 here, central atom is carbon, is attached to 4 different carbon, and they are all single bonded. So this molecule is going to be nonpolar. Now, for chloromethane, you have a central atom of carbon attached to 3 hydrogens and 1 chlorine. So one element here is different, or one bond is different than the other 3. This is going to be uneven distribution of electrons. For uneven distribution of electron, your molecule is going to be polar. Why? Which area of the molecule is going to be partially negative? The side of the molecule that carries that high electronegativity element. The other side of the molecule is going to be positive. So basically, you are counting as pulling electron toward the chlorine for chloromethane. Even if you had dichloromethane, so let's say you have Cl, Cl, H, H, or if you draw it this way, Cl, Cl, H, H. Both of these molecules are polar because we're just going to count one rule. We are looking at the central atom. Is it attached to all same or different elements? If it's attached to different elements, so your molecule is going to be polar molecule, regardless of how many are they. So you have 2 chlorine, 2 hydrogen. Central atom is attached to 2 different elements, 2 different type of elements, so your molecule is going to be polar molecule. But this one, because carbon is attached to 4 chlorine, is going to be polar. Exactly. If the dipole cancels out, that's just the example of the carbon dioxide. The dipole, or the difference in electronegativity between carbon and oxygen on the right side, is the same as the difference in electronegativity between the carbon and oxygen on the left side. So basically, what is happening here is, like when I'm in the class, I say, okay, if I'm standing straight, I'm nonpolar. I'm stable. But if I have two people pulling me, and one is weak and the other one is really strong, so I'm going to be tilted to the side that the person who is strong is going to pull me to the other way, and that makes me like unstable because I'm going to be tilted to the side that is pulling strongly, and I'm going to be considered unstable. Uneven distribution of forces, uneven distribution of electrons, and it's going to be polar. So if you're talking about the 2 carbon and the 2 chlorine and 2 hydrogen, yes, for the 3D structure that we are going to look at, this molecule with the 3D structure is not flat, that you can distribute like on the left and the right side. So we are, for the 3D structure, they don't actually cancel each other's effect, and it's going to be polar. And very good comments there. For pair of unshared electron, how is going to determine if the molecule is polar or non-polar? If you have pair of unshared electron on central atom, your molecule is going to be polar because it's not same as other bonds. So for water molecule, you have 2 hydrogens and 2 pairs of unshared electron. So basically, to determine the molecule is polar or non-polar, you must have proper Lewis structure. Because if you don't have proper Lewis structure and you just say, okay, H2O, going to put oxygen and then hydrogen on one side and hydrogen on another side. That is not the structure for water. That's not the Lewis structure for water. When you draw the Lewis structure for water, you have 8 electrons that you have to distribute. So 2 of them is going to be, 2 pairs is going to be used to form the bond, and then you have 2 pairs, the other 4 electrons assigned to the oxygen. Now you count the number of domains as pairs of unshared electron and the bonds. So you have 4 domains here. 2 of them are pairs of unshared electron and 2 of them are sigma bonds. So since they are different, water molecule is going to be polar. So in general, if you see, on the previous slides, we saw nitrogen carrying 1 pair of unshared electron, oxygen carrying 2 pairs of unshared electron. And if you have only like 1 chlorine as a central atom, if the central atom has pairs of unshared electron, because pair of unshared electron for domain elements is not written in the structure of molecule. So if the central atom has pair of unshared electron, your molecule definitely is going to be polar. Just to verify, carbon dioxide and carbon tetra are nonpolar because the elements surrounding the central atom are the same. Yes, and there is no pair of unshared electron in the central atom. Yes, very good. Okay, any questions about ionic polar, nonpolar? See what happens when the molecule is polar. In this case, chloromethane is polar because one of the elements attached to central atom is different than the other 3 elements. So electrons spend more time around that high electronegative element. So in this side of the molecule is going to be partially negative. The other side of the molecule is going to be partially positive. So electrons spend more time around chlorine. I kind of covered the formal charge and the Lewis structure, but we are going to just look at these examples also. In case if you have questions, we can answer the questions. So this one is showing step by step how to draw the Lewis structure. First, you count the total number of valence electron. For PCl3, we have 3 times 7 coming from chlorine, that's 21, and you have 5 from phosphorus because it's in group 5, plus 5 is going to be 26 electron you have to be worried about. 6 of them is used for connecting, and then you have 18 of them being used for the chlorine, the side elements, and 2 is left that if we would go to the central atom. So your central atom has lone pair. Now, is this molecule polar or nonpolar? It's polar. Very good. And why is polar? Because of the lone pair in the central atom. So the lone pair on the domain atom is not counted toward polarity of the molecule, but the lone pair on the central atom is going to be is counted for the polarity. So your molecule is polar, and the pair of unshared electron that you have here actually gives like it partially negative charge where you have pair of unshared electron, partially negative charge where you have more electronegative elements also. So it basically makes this molecule to be slightly nucleophile, or being able to share this lone pair with something that has positive charge. Very good. Okay. Using multiple bonding as a solution to satisfy the octet for each element. So if we start with the hydrogen cyanide to begin with, we have 5 from nitrogen, 4 from carbon, and 1 from hydrogen, and that adds up to 10 electron. When we form the bond, we use 4 of them, 6 is left, nitrogen takes it. Carbon is not satisfied. Carbon is tetravalent. It must have 4 bonds. It must have 8 electrons. So first we give 1 pair of electron. If we give 1 pair of electron, it's going to look like this, with nitrogen being satisfied and the carbon still not satisfied, because carbon still has 6 electrons only. So we are forced to form 1 more bond between nitrogen and carbon. When we form that, it's going to be triple bond, formation of triple bond. And what is unique about shared electrons, when you have shared electrons, they are going to count toward both atoms. Just like I use usually the example of, if I have 2 children, I can say for sure that I have 2 children. I don't have to say my husband and I have 2 children. My husband separately can say I have 2 children. So shared electrons, they are unique because they are shared. They are counted toward both nucleuses, and also they are loved by 2 nucleuses. So shared electrons are kind of in specific unique position because they make the molecule more stable, and the stronger, the greater number of shared electrons between the 2 atoms, it makes that bond stronger also. So when you have a single bond, double bond, triple bond is going to be stronger because it's sharing 1 pair of electrons. Unshared pair of electron, that just belongs to one of the element, that makes that element more reactive because it has pair of electron to do something with it. So it acts as a nucleophile, or it can donate that. It can act as a Lewis space to donate that electron. So just other points about the Lewis structure when you are counting the number of electrons. So shared electron counts toward both elements. Which one? Now I think it's time to answer your question about major and minor. Which one of these Lewis structures look better to you? 1, 2, or 3? For all of them, you have 8 electrons, 8 electrons, 8 electrons for each, 8 electron, 8 electron, and 8 electron for each. Which one is the best? 3? Okay, let's see what's the benefit for 3. For 1, what is wrong with 1? First of all, we have huge charge separation. We cannot have -2 and a charge and a +1 if we have a choice of 0. Okay, if we have a choice of 0 charge or less charge separation, the -2 and a +1 existing in the same molecule, it makes this resonance, even though it might be, but it's going to be very minor resonance, because this situation, when you get 2 negative charge and 1 positive charge, first of all, oxygen and halogens, again, or halides, they do not like positive charge. So if you have a resonance structure, a Lewis structure that you're giving positive charge to oxygen, forget about it. Unstable. So it's not even contributing. When it comes to comparing 2 and 3, for 2, after you calculate the formal charge, and I hope that everyone knows how to calculate the formal charge, or you ask me questions, nitrogen is given -1, Oxygen is given 0 charge. Now, which one has higher electronegativity? Nitrogen or oxygen? Oxygen has higher electronegativity. Thank you for your response. So, which one is better off to have that negative charge? Oxygen or nitrogen? Because basically that's the difference here. So in this case, nitrogen with the negative charge, in resonance 3, oxygen carries that negative charge. So to answer your question earlier, resonance 3 in this case is going to be major, and this is going to be minor. So we have a minor resonance and we have a major resonance here. So we do have two resonances. These two resonances definitely look much better than the resonance 1, but this is going to be major resonance, this is going to be minor resonance. Even both of them, if both of them forms, your molecule is going to spend most of its time in this form of 3, and less time like 2 and never like 1, because oxygen does not like the plus charge. It makes it very unstable. The reason I emphasize on that, because we are using this in chapter 6, 7, 8 to remove hydrogen, because oxygen cannot, with the H plus, because oxygen cannot handle that plus charge. We see this a lot in organic chemistry, that oxygen does not like positive charge. Okay, hydrogen and halides is going to carry only one sigma bond, no double bond, no two bonds, one bond only, and we talked about this already. Unless you have questions, and these are some of the examples. Now, the backbone of the molecule is going to be given to you, because for exam 1, you don't have the structure formula for every molecule. So after you learn about the functional groups, then you can build the backbone yourself. Like if you know the molecule is ether, then you have carbon-oxygen bond. So that's the case that you know the oxygen needs to be shared between 2 carbon, or 2 carbon needs to be attached to the oxygen. Otherwise, if you were given just 2 carbon, 6 hydrogen, and O, you might have draw that like a CH3, CH2OH, or this functional group of ether, but it has to be specified. They're talking about the ether or they're talking about the alcohol. So the backbone, for now, it will be given until you learn about the functional group. Okay. Common pattern again for the organic molecules. We have, if you had carbon with a 1 positive charge, what is the problem with that? Carbon with 1 positive charge, that means it has only 6 electrons, so it's not going to be stable. So there are some molecules that your atom, your element doesn't have the octet. The octet is not satisfied, and in that case, you have no choice. Let me give you an example of BH3. To draw the Lewis structure for BH3, B, H, H, and H. 3 valence electron is coming from boron, and 3 times 1, that is 3 valence electron from hydrogen. So you have, in total, you have 6 valence electrons. The first step would be connect them. So let's connect here. How many electron is used? 6 electron is used, and 0 electron is left. When there is 0 electron left here, what is the solution? Hydrogen is satisfied with the electrons because hydrogen with 2 electrons is satisfied. The octet rule, or the rule of 2, it goes together. Helium is a noble gas, stable, so hydrogen, if it's just like helium with 2 electrons, is going to be stable and satisfied. Boron here has 6 electrons only, is not octet satisfied, but that's how it's going to stay because there is no electron coming from hydrogen to form the double bond, or there is no extra electron borrowed from somewhere to give it to B. So basically, this is going to carry empty orbital. When you have a molecule like this with empty orbital in organic chemistry, it has a huge advantage to that. In inorganic chemistry, you might look at this like very unstable molecule, but in organic chemistry, this can be used as a Lewis acid. So when you have your Lewis acid with empty orbital, it can accept electron, or it can attack something that has extra electron. This is like Lewis acid is used as a catalyst in many reactions you will see in future chapters. But for now, just know that is exception to the octet, and it exists and is used for reactions as an initiator or as a catalyst. Another example of that is aluminum chloride. So for aluminum chloride, when you draw the Lewis structure, you get 3 pairs of unshared electron on each chlorine. Like that. So if you look at chlorine, all 3 chlorines are satisfied. If you look at the aluminum, aluminum is not satisfied. And if it's not satisfied, what can we do at this point? Can we have a double bond? Okay, if we have a double bond, that means that double bond has to form between chlorine and aluminum, right? What did we talk about? What did we say about chlorine? Halogens in general. How many bonds that they can form? Only single bond, right? Only single bond. So even though, thank you, Jordan. So even though chlorine is, it carries pairs of unshared electron, is not going to bring the one pair of unshared electron to the center to form double bond, because chlorine is not allowed to form double bond. So since chlorine is not allowed to form double bond, this molecule is going to stay the way it is. That's exception to the octet rule, and we are taking advantage of that. Aluminum chloride is a good catalyst, and you will learn and use it a lot in organic reactions in the future. Resonance structures. Resonance structure, we have 2 resonance structure here for or the resonance forms of the resonance hybrid. This is a combination of the 2, the hybrid resonance. That means the bond between carbon and nitrogen, it's not a definite double bond or single bond because it goes back and forth. So you can represent it with the dashed line. Sometimes on the pair of electrons is on the nitrogen, and other times is double bond between the carbon. This example we actually started with the acetate ion. When acetic acid is added to water, is going to lose hydrogen. It becomes acetate ion with the negative charge, total of 24 electrons. Acetate ion, when the electron distribution takes place, you get a negative charge for oxygen, and two pairs of unshared electron with one double bond for the other oxygen, you do have a choice in this case, because two oxygens are identical, to have double bond with the other oxygen, and now you have two resonances. Which one is major, which one minor? In this case, because the formal charges stay the same for the two resonances, they are both contributor, and it's like a 50-50. There is no major and minor. Okay. You have this choice here. Why is not acceptable? The answer is up there, but I just want to emphasize it. If you have a resonance that you are giving to it nitrogen, carbon, or oxygen, or any element in level 2 more than 8 electron, that is a no, just like giving plus charge to oxygen. This is even worse because you may force oxygen to lose electron, but you cannot force nitrogen to get more than 8 electron. This is giving 10 electron to nitrogen. It's going to make it very unstable. It doesn't exist, or the percentage is going to be less than 1%. So the reason, just like carbon, nitrogen is in level 2, has only one s orbital and p subshell, total of 8 electron in the valence shell. No more electron is accepted. But if you had like sulfur, level 3 could have more than 8 electrons. Okay, so you have a major and minor. One more example for major and minor, just to make sure. For this, the major structure, you have 8 electron for carbon, 2 electron for each of the hydrogens, and then you have 8 electron for nitrogen here. In the other resonance, you have 6 electron for carbon, 8 electron for nitrogen. There is a problem here, right? You have only 6 electron for carbon. If you have only 6 electron for carbon, that is going to be a minor contributor. Because you have plus charge on nitrogen here is not good. This is not good. Having plus charge in nitrogen is not good. But why this counts as major and this one minor? That goes to the priority. Which one takes the priority? The octet or the charge distribution? So in comparing, one is bad, one is worse. Now, which one is worse is like if you have an element that does not satisfy the octet. That's why this resonance of the methylamine is going to be minor, because the octet is not satisfied. Then you have your formaldehyde, the same thing here for formaldehyde, minor, because you don't have that. Okay, these two structures are not resonance. Can you tell me why they are not resonance? When you are forming the two resonances, there should be a benefit to the molecule. That benefit is either distribution of the charge or distribution of formal charge. In this case, there is a distribution of formal charge. So these two are valid resonance forms, and they do form and they stabilize each other. The greater number of resonances, the more stable the molecule is. And for these two, you are not getting any charge distribution. The charge is not being distributed. So these two are same molecule. They are not resonance. Okay. How do they we write the structures for a molecule, how many different type of formulas do we have? One is called molecular formula. So if we have C2H5OH, this is molecular formula. Okay, that is just showing and defending your question about why should we have that resonance if the octet, if the carbon doesn't have the octet. That is just emphasizing on which one is a minor resonance, which one is a major resonance. The other problem for that example, because nitrogen had a plus charge, nitrogen does not like plus charge and is trying to push it over to the carbon. So it's going to happen, but is not going to stay, is not going to be stable. So it kind of goes back and forth, but less time for minor resonance, more time for major resonance. So it's going to stay more, the molecule is going to spend more time as the major resonance and less time for the minor resonance. What type of information you are getting from molecular structures? So examples of C2H5OH or C2H6O, same thing. This is molecular formula. Molecular formula is going to give us information how many different elements you have and how many of each you have. Then we have a structural formula. In a structural formula in organic molecule is going to show the connectivity between the carbon and every element. So you have your hydrogens bonded to carbon. So a structural formula, it shows the connectivity between every element. This is the complete like structural formula. Another formula that is used in organic chemistry, because you see it takes time to draw all this, is condensed a structural formula. When it's condensed formula, you're not going to show the bond between carbon and hydrogen. You just say there are 3 hydrogens bonded to this carbon, and you have 2 hydrogens bonded to this carbon, and 1 OH bonded to this carbon. So that's condensed structural formula. Often they don't even have to use this dash line here. They don't have to show the bond between carbon and carbon, but you could use the carbon-carbon bond. You could show the carbon-carbon bond, but you are not showing carbon-hydrogen bond, and it is condensed. So we have molecular formula, structural formula, and condensed structural formula. We also have another formula is line angle. For the line angle, a structural formula. So you are using line and angle to show your molecular, to show your molecule. Often is used for cyclic system, or if you have like a molecule with too many carbons. So instead of me writing like a CH2, 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 and CH2. Basically, you have, these are single bond. This form is called a cyclic molecule because carbons are kind of forming a closed chain here. Instead of this showing all the CH2, CH5 CH2s here, we can draw just this line and angle. Exact same structure, less time, because you have your molecules in organic chemistry, they are sometimes they have too many carbons or too many elements. They try to save time. So how do we know what is included here? Every angle includes a carbon. Every angle has a carbon. How many hydrogens do we have to have there? as many hydrogen to satisfy carbon. What is satisfaction for carbon is 4 bonds. So if the hydrogens are not shown there, how many hydrogens should I bring to this carbon? Is going to be 2 hydrogen, 1 and 2 hydrogen. How many hydrogen this carbon needs? 1 hydrogen, 1 hydrogen. So you just have to be kind of smart and say you have 2 hydrogens on each carbon and there is 1 carbon on each angle. So let's say we have this line angle. How many carbons do you have there? If you have a line angle here, very good. Your molecule starts with carbon, it ends with carbon, and every angle has a carbon. How many hydrogens do you have there? It starts with 3 hydrogens because there is 1 bond between carbon and carbon, so there must be 3 hydrogens here. It ends with 3 hydrogens, and the others, they must have enough hydrogen to get 8 electrons for the carbon. So you have your CH2s on each angle and CH3 beginning and end of the chain. If you have a molecule that is like this, what does that mean? It means you have 1 functional group here, one that is different from carbon, carbon, and carbon hydrogen single bond only. So we must show that double bond there. And in this case, how many hydrogen you need to add to this angle is just 1 hydrogen here, and it's only 1 hydrogen here for this carbon, because this carbon already has 3 bonds, 1 single bond, 1 double bond, that gives 6 electrons. You only need to add 1 hydrogen. So that's another representation of the organic molecule and is known as line angle. So with the line angle, you have your chain. It is open chain. It starts with carbon, ends with carbon, and every angle has a carbon. So if you draw this square, in math, it's just a square, but in organic chemistry, that means 4 carbon and how many hydrogens? 2 on each, so 8 hydrogens. Very good, thank you. Okay. We have the name for the compound, 2-butene, structure formula, and then we have the condensed structure formula. If we have this condensed structure formula, how do we know there is a double bond there? Because you have the 2 options. So if this is given to you, you might just consider, well, there's a typo. There must be 2 hydrogens there instead of 1 because it doesn't make sense. Carbon must have 4 bonds. The other possibility, or the truth, is that this carbon 2 and carbon 3 carries a double bond. So if the number of hydrogens are limited, you don't have enough hydrogen to satisfy the 4 bonds for carbon, you must use multiple bonding. When you are writing the condensed structure, you must show the functional group. So your CN triple bond, this is showing the functional group. And then just know it's kind of too early, but it's very important for you when you are writing the condensed structure. If it's aldehyde, C double bond oxygen and H. So this is the functional group for aldehyde. When you are writing the condensed formula, you would write CHO. CHO, this is the functional group for aldehyde. If you have alcohol, if you had alcohol somewhere your alcohol, let's say if you have OH as alcohol, you would write COH. So that's the difference between CHO and COH. A example that is usually used in ACS exam to trick the students. My students at NOVA, they always had trouble with this. Organic 2 students, I'm not talking about like beginning, the second day of the organic chemistry. Even for organic 2, they always make a mistake, and I always have this question on their exam, like as a condensed formula, as a CHO, and then not everybody, but I get a lot of wrong answers based on counting this as alcohol. It's not alcohol. So there is a difference between CHO and COH. COH is functional group for alcohol. CHO is functional group for aldehyde. So when you're writing the condensed formula for aldehyde, you have to pay attention to this functional group for ketone, CO double bond between the 2 carbon, and the aldehyde, it's the CO double bond attached to 1 hydrogen and 1 CH3. We will talk about functional group in chapter 2 soon. Any questions about line angle, or what does the line and angle means, and why do we have to show the double bond here? Why do we have to show the oxygen here? In condensed formula, we have to show the functional group, and we have to show double bond or triple bond. Double bond, triple bond, it counts as the functional group. So if you have a structure of, if you have a line angle structure and there is a attachment here on one of the angles, that means is actually 1 carbon. So if you break this, that means you have like 2 carbon attached to this cyclic system, or a carbon chain is attached. So if you have these, that's like 1, 2, 3 carbon is attached to this carbon. Ethyl group attached, or propyl group is attached to the carbon. Okay. What's the difference between molecular formula and empirical formula? A molecular formula is for H2O2, hydrogen peroxide. Empirical formula is going to be H1O1. Butane, C4H8, molecular formula, and the empirical formula for that is going to be C1H2. Empirical formula is the lowest ratio of the elements, or it shows the lowest ratio of the elements in a molecule. Molecular formula, it shows the actual number of elements in the molecule. How do they go from empirical formula to molecular formula? You must have molar mass. So if you have this as the empirical formula, and you know the molar mass is 48 plus 8, that would be 56. Is that right? So if you have 56 as the molecular weight, and that's the empirical formula, you find the mass for empirical. So that's 12 plus 2, that's 14. And then you say 56 divided by 14 is going to be 4. 4 is the n value. That means your empirical formula is times 4 is going to be molecular formula, or your molecular formula is divide by 4, or each of them. So this is the number that you are going to, the n value that you multiply by each of these subscripts to get to the molecular formula. Just to remind you, we don't deal with this type of problem a lot, so I'm not going to take too much time for this one. I want to just mention that molecular weight, it can be determined with the experiments that you learned in general chemistry, like freezing point depression, that you use naphthalene as a solvent and you add the unknown, and the more the the freezing point is depressed, that means the molar mass is less, or using the vapor for gas laws and to find the molar mass. But there's more advanced ways to determine the molecular weight, and that is the mass spectroscopy. You just sample to machine and you get the molar mass with just in less than 2 minutes time, you get your molar mass. And when you have the molar mass and you have your elemental analysis, so let's say you know your compound has only carbon and has only hydrogen, and the ratio of carbon to hydrogen is 1:2, then you have your empirical formula. Let's say if you have a C3H8, what would be the empirical formula for that compound? In this case, you cannot divide 3 and 8 to the same number. It doesn't have the least common multiple. So what you do is going to be C3H8. Molecular and empirical formula is the same, but sometimes molecular formula is different from empirical formula. Do you have any questions? Any questions? I tried to make some changes to the syllabus as I promised yesterday. I fixed the date for the exam. One is going to be on the 26th, even though I had a 21 and in the syllabus, and I should have gone with that. But since I promised 26th, I kept changing it to 26. Yes, exactly. 56 is from C4H8, that's the molecular weight, and then 14 is the empirical weight. So you divide the molecular weight by the empirical weight in order to get the value for N by what number you should multiply each one of these subscripts to get into the molecular formula. Molecular formula is a multiple of empirical formula, but that factor of the multiplication, it needs to be calculated. How do you calculate? You get the molar mass and you get the empirical mass, and you find that N value. The other changes that I made to the course, I created a discussion board called a student cafe. That's for your questions, for your classmates to submit your question there and get help from your classmates. Hopefully we get that, and then if I see incorrect information, I will make sure to correct it. The other change was I create a submission folder for your co-op group members. I know a few of you already sent me your email with the names. I just want to make sure that I have them all in one place. I'm asking you if you could please submit the names as just a file, make it small, like a Word document or whatever. You just go in there and add your file into that folder, so I know I have every group in one place, so I don't have to look through emails later on to find who was the group member. When I'm checking before May 19, which is the last day to get the group, to make sure that everyone is in one of the groups at least, is easier for me and is all in one place. So those are the two folders that are new in your D2L show. One question I have for you: were you able to access the recorded session from yesterday? Yes? Very good. Because no? No. Okay. So that means I have to release I kind of have to copy the link, and I'm not going to send email. I'm going to put in announcement. So I will post the link for the recorded session in the announcement. So you can click on that and you can access to the recorded link. I was waiting for you guys to tell me if you can access or not. Often when you are registered for the course and is the previous session, you just click on all sessions when you go to Blackboard Communicate, and it should be there. And if it's not there, okay, if it's not there, then we can just I can send the link to you. Amanda, yes, the group names only. Okay, where is the folder for the group member submission? There is a folder, is the assignment folder. I think I named it as a co-op group. File posted. That should be just. It's new. I created today, and if it's not saved, I will check it again. But there is a folder with the co-op folder. Yes, co-op group members. You just submit your file there. Okay. Let's see what's the next topic for you. Definitions for acids and base. Is the quiz to be taken during the class time? After the class, right after the class. Because that way, at least I was actually happy when I was looking at the schedule. I said, okay, like we are going to save some time for quiz and save the time for the exam, because you're taking after the class. So it won't be during the class. Definition for acids and bases. Arneous acid, it releases hydrogen in water. Arneous base is going to release OH in base. Then we have other definition for acids, that is Lewis acid or Lewis base. Lewis acid is going to accept electrons, and Lewis base is going to donate electron. Lewis acid and base definition is used more often in the in organic chemistry, just like the example of BH3 that I gave you. BH3 with the empty orbital, it can accept electrons. This counts as Lewis acid. And your Lewis base, say you have ammonia, NH3, it can donate electron. Pair of electron is there. It can donate electron. That is a Lewis base. We do have other names for this in organic chemistry. This NH3 is called a nucleophile. That means it likes nucleus. What do you find in the nucleus? In nucleus of the atom, you find plus charge. So when you say nucleophile, that means it likes plus charge. That means it must have a negative charge already, or it must have pair of unshared electron already, because it's looking for plus charge. So pair of unshared electron is going to make the molecule a Lewis base. That means pair of electron donor. Empty orbital, like the BH3, is going to make the molecule Lewis acid. This means pair of electron acceptor. And you all know about the pH less than 7 and greater than 7. I don't think you want me to spend time on that. Bronzed-Lowry acid base. This one also has more application in organic chemistry, because if the acid is weak and donates proton, is going to change to conjugate base, and that conjugate base is going to be very strong. So the Bronzed-Lowry acid base or acid conjugate base pair is the one that we are going to use in organic chemistry. The difference between an acid and a conjugate base is just one proton, and only one proton, no two protons. Like this is a proton donor, that is the acid. A conjugate base to that is conjugate base is going to be NO3 minus. The difference here is -1 hydrogen. So this is the pair of acid conjugate base. A strong acid, weak conjugate base. Let's see if I have somewhere room to. This is a base, and this is going to be conjugate acid. So we have base, this starts with the base, and this is the conjugate acid. Basically, you're adding one hydrogen to get one hydrogen only to get to the conjugate acid. This conjugate acid, is it weak or strong? Can you tell me if this CH3OH, and if you don't know, is alcohol, is it weak acid or strong acid? Weak acid. The conjugate base is going to be strong. So this is weak. Conjugate base is going to be strong. If you have a conjugate base to a weak acid, then you know you have a strong base. A strong base is looking for a positive center more aggressively. So this is also in organic chemistry is known as a strong nucleophile. That means it's looking for positive center. Because I know most of you already know the acid base and the conjugate acid conjugate base. I'm emphasizing more on the application of these definitions in organic chemistry. And water has amphoteric property. It can act as acid. It can act as base. Same thing for ammonia. Ammonia can accept hydrogen or H plus because it has pair of unshared electrons. It has hydrogens. It can donate, but is a base, is a weak base. If it donates, if ammonia donates hydrogen, is going to change to NH2 minus. NH2 minus is going to be very strong base because this is already weak base. You're removing hydrogen is going to make it very strong base. So this is a strong base. Acid strength and pKa. How is pKa and pH related? pKa is for weak acids. pH is for every acid is for strong acid. pKa, just like pH, the lower the number, the stronger the acid is going to be. So pKa of, let's say, acetic acid is 4.76 for acetic acid. For pKa for ethanol is like 16. For ethanol, CH3OH, or is similar to this. For methanol is 16. So which one is a stronger acid? Acetic acid or ethanol? If you have the pKa already, you just look at the number. The lower the pKa, the stronger the acid is. If you don't have the pKa, then you have to look for factors that is going to determine which acid is stronger, which one is weaker. One thing you have to keep in mind and know it by heart, and you may want to write in a few times so you don't forget, is that the value for pKa, if it's given, fine. If it's not given, resonances is going to make the molecule more stable. We talked about that before. The more stable conjugate base, that gives a stronger acid. So if you have an acid that is losing hydrogen, it becomes conjugate base. Let's see if I insert a blank page here. Unfortunately not. Okay. I need a blank page. What happened? Okay, going to write here. So if you have CH3OH losing hydrogen, it's going to change to CH3O minus. Three pairs of unshared electrons. Can this form resonance? Can CH3O minus form resonance? No, no resonances. Acetic acid, this is acetic acid, is going to form the acetate ion because you have two oxygen here to share the double bonds, is going to form resonance. So you have your second resonance here as the O minus and O with the two pairs of electrons. So for alcohol, after losing hydrogen, there is no resonance. For acetic acid, after losing hydrogen, there are two resonances. I just want to make sure that you can connect these dots together. Which one is more stable? Conjugate, this is the acid, that's the conjugate base, but for your conjugate base, you have two resonances. For methanol, you have your acid and you have your conjugate base. For your conjugate base resulted from methanol, there is no resonance. So if there is no resonance versus for acetic acid, you have two resonances, the conjugate base from acetic acid is a lot more stable because of the resonances. And because it's stable, that goes back to a strength of the acid. The acid is stronger if the conjugate base is stable. So acetic acid is stronger than methanol. If you had the pKa value for that, for methanol is 15.5, I kind of approximate 16, but for acetic acid is a 4.74. Lower pKa, greater pKa for methanol. And the reason is because of the resonance of the conjugate base. So that's one of the factors. The more stable the conjugate base, the stronger the acid is going to be. So pH, it shows the acidity. It can be changed from 0 to 14, and it depends on the strength of the acid. It depends on the concentration of the acid. But pKa is a constant value that shows the equilibrium constant for the acid. Based on this formula that we had earlier, it shows the concentration of the product over concentration of the reactants. And if you take the negative log of K value, you end up with a pKa value. So pKa shows the strength of the acid and how ionizable is your acid. If it's 100% ionization, is going to be a strong acid. Less than that is going to be weak acid. But among the weak acid, which one is weaker? So lower pKa equals more stable. Lower pKa, that means is a stronger acid. That means the conjugate base is that. This is the question. I don't know everybody see the question or not, but when I read the question, I give the answer. I want to know if everybody doesn't see the question, then I can read the question first before giving the answer. Do you see the question if someone posts the question on chat? Yes? Okay, then good. So lower pKa equals more stable. It's yes, but at the same time, it has to be more clarified. So when you have lower pKa, that means your acid is strong. That means your conjugate base is more stable. So more stability goes to the conjugate base, not the acid itself, because that acid that has lower pKa, that means it's more reactive. So it's going to donate the hydrogen to change to the conjugate base, and your conjugate base is going to be more stable. The strength of the acid. How do we know acid is weak or is strong? There are few factors. One was the resonance. The more resonance for conjugate base, the stronger the acid. The other factor that you could use is the electronegativity. But please use the electronegativity only across the periodic table. So if you are going from carbon to fluorine, CH, NH, OH, F, HF, the higher the electronegativity of the element attached to hydrogen is going to be a stronger acid. Okay? It's going to be a stronger acid. And the conjugate base is going to be more stable. So if HF is your acid, conjugate base is F minus, is more stable than if you had the H2O, for example, and H2O losing hydrogen is going to change to OH. You see, this is a strong base, is not stable. So H2O is a weak acid. So you can go either way. You could say you have a stronger acid, the conjugate base is more stable, or you could say because the conjugate base is not stable, is very reactive, the acid must be a weak acid. So comparing H2O with HF, you compare the electronegativity. So you justify the electronegativity with electronegativity. You say fluorine has higher electronegativity than oxygen, so HF is the stronger acid compared to H2O. Down the group, you choose you justify the acidity based on size of the element attached to the hydrogen. So if you have HCl and HBr, the greater the size, the stronger the acid is going to be. Because if you compare the Cl minus to Br minus, which one is going to be more stable? Br minus is going to be more stable than Cl minus. Why? Because Cl has 3 shells, Br has 4 shells. Br is greater in size. It can handle that negative charge more. Or you could just say, because it's not general chemistry, you could just say we are using the size factor down the group. So if you have HCl, HBr, HI, the higher the size, the greater the size of the atom attached to hydrogen is going to be stronger the acid. Another factor is hybridization. Hybridization is the more of the S character, the stronger the acid. So if you have like a C triple bond CH, this carbon has a sp hybridization. So this hydrogen is more acidic. The more S character of the carbon that carries the hydrogen, that means sp has more S character because one S is mixed with one P. For sp2, you have one S 2p orbitals. For sp3 is one S 3p orbitals. So S character for sp is greater than sp2, greater than sp3. So the greater the S character, the stronger the acid is going to be. So you have the sp for ethine is going to be a stronger acid compared to ethene, because this is a sp2, stronger acid compared to ethane. And we look at the pKa value also here. It's a very high pKa. High pKa means weak acid. And then the size factor here is explained. Again, resonance stability is explained. I'm going to just say it one more time. The factors. You can use the resonance, the stability of the conjugate base. That's one factor. You could use the electronegativity if you are going across the periodic table from left to right. Electronegativity of the element increases. If it's attached directly to the hydrogen, that is going to make a stronger acid. Size factor up down is going to be increasing the size. The strength of the acid is going to be higher, and the S character. So those are the 4 factors that can be used to determine if your acid is weak or strong, or how weak or strong it is. Electron withdrawing group is going to increase the acidity. So if you have carboxylic acid with no chlorine attached to it, you have a carboxylic acid with bromine attached to it, chlorine attached, or fluorine attached. The greater the electronegativity of this element attached, the stronger the acid is going to also, the substituent, if you have high electronegativity substituent, is going to increase the acidity. The other factor, a secondary factor here, is the distance also. So if instead of 2 carbon, if you had 3 carbon, so if you had CCCCOH, your fluorine is on the 2nd carbon here. If I move the fluorine to 3rd carbon, comparing this with this, fluorine closer to the acid functional group, fluorine further away from the acid functional group, this is a long distance effect. So comparing these two, the top one is going to be more acidic compared to the bottom one, because your electronegativity is the same, but the distance is further away. Questions? Any questions for me? How many questions will be on the quiz tomorrow? 10. I make it easy. 10 questions on the quiz. 10 multiple choice questions on the quiz. This factor here, the arrow sign going from rich to electron poor, keep this in mind. We don't need it for the first 5 chapters, but if you learn now, hopefully it's going to stay with you forever. When you are drawing these arrow, you point the arrow to the side that has less electron density. So the curve, it should say, starts from where the electrons is going to end up with. So electrons is moving from electron rich to electron poor. Let me look at your questions. How many questions? 10. The quiz timed. Yes, but it's not going to be strained. So end of the day, and it will be due end of the day. Yes, I'm going to make it 1 day. Yes, because you have other things to worry about the next day. Your chapter 2. When do we know you're going to have a live lecture for lab? What do you mean? Yes, we are going to have live lecture in the lab tomorrow. Tomorrow, definitely, we have to do the first experiment in the lab. It starts at 10 o'clock. So tomorrow, basically, I'm going to have my lecture also from the lab. So you have is not going to be, time for me to go to the lab. So we start the lab at 10. So for those of you who have lab right after the lecture, you can take your quiz after the lab. VSPR geometry naming on the quiz, that is in chapter 2, if there is anything, but not chapter 1. Quiz is timed. Yes, the quiz is timed. Any other questions you might have for me? Thank you. I'm glad that we didn't have at least technical problems today. And I'm here to answer your questions. If you have any questions, you let me know. Assignments for OR app is already released. There is no restriction. You can work on it. And that would probably help you for your quiz too. And the assignments for co-op, it will be released based on the table. If it's today, it's going to be today. Or if it's tomorrow, it's going to be tomorrow. But we will have it released. I'm going to follow the syllabus for that. So do we get a study guide for quiz? No, is it the whole chapter?